Hi everyone, welcome to Last Minute Maths. In this video we're going to look at some of the material in the GCSE Physics Paper 1, Particles and Matter, so the particle theory of matter. Now, before starting, just want to clarify one thing. According to the advanced information, the pressure, gas pressure and pressure rules are not to be examined, but I'm including it in the video at the end. So those of you who don't need to do it, certainly the AQA one, excluded, but IGCSE, I think that is still examinable. So in any case, you may choose to skip the last part, last minute or two at the end. But do refer to the advanced information, make sure you're covering the right bits. Okay. All right, just to dive into it then. The particle theory of matter. All matter made up of particles, all right, as we know, which are going to be in the form of atoms or molecules. All right, so either single atoms, like in a pure substance, or molecules in compounds and mixtures and things. The first thing that we need to cover is density. All right, now that's a measure of how much mass is contained, right, in a given volume, so per unit volume, if you like. For that, you can also read in a physics context is how much matter there is. So mass is an indication of how much matter. So density, all right, the symbol for it is a Greek rho, all right, is mass divided by volume. Now in SI units, as I'm sure you all know, mass is always in kilograms, all right, and volume will be in cubic meters. Okay, so the units of density are kilograms per cubic meter. All right, and watch out, some of the questions can come up in different forms. The units can be changed. So for example, grams per cubic centimeter. The way to convert, remember, and I know this is basic, but it's worth putting it in. 1 kilogram, 1,000 grams. 1 meter, you know it's, oops, I've got a mistake there. Hang on. All right, there we go. 1 meter is 100 centimeters. All right, therefore, a cubic meter is basically 100 centimeters times 100 times 100, which is 1 million cubic centimeters. All right, so that is the same as 1 times 10 to the 6. All right, cubic centimeters for every meter. So if you need to, make sure you convert correctly between units. All right. Okay. Density of solids. Now this can come up in a practical question if you wish. The way to do it is to measure the mass using an electronic balance, right? A mass balance. And then to find the volume, all right, for regular shapes, meaning cubes and cuboids, so that you can actually sort of measure the dimensions and work out the volume that way. If it comes up in something that's like practical oriented, then mention things like vernier calipers and or a micrometer for even smaller measurements. And then use the, length times width times height equals volume, all right? Basic stuff. For liquids, right, you measure the volume using a measuring cylinder. Now in this one, again, in a practical sense, if you have a measuring cylinder, oops, let's do that again. And for that, remember the liquid is going to be like that, and you have to measure it at the bottom of the meniscus. That's an extra mark for you in a practical write-up. You get the word meniscus in there, all right, to avoid error. So using a measuring cylinder, and then measure the mass of an empty cylinder, right? That's effectively zeroing the mass balance, and then with the liquid, okay? The difference is going to equal mass of liquid, Okay. One thing that I need to go back to here, which is important, and it does come up in questions, is for irregular shapes, odd-shaped objects, you need to put it into, I don't know, a big beaker or a container of water. All right. And it's got to be full to the top. And then you immerse your odd-shaped object in there, and an amount of water is going to be displaced. All right. And that will tell you the volume. So displaced liquid equals volume of object. Okay. Right. Hopefully that covers that. Moving on. Density, one thing to note about it, changes with temperature. All right. And that is very important for the next thing that we're going to be talking about. And higher the temperature, right, the lower the density. So increasing the temperature will reduce the density. Okay. So, example, hot air balloon. Okay. And that sort of thing. Have I spelled balloon right? I have no idea. Right. States of matter and change of state. All right. Now, matter exists in 3 states. All right. And solid, liquid, and gas, as we all know. There is a 4th one called a plasma, but you don't need that for GCSE, so we're not going to go there in this video at least. Okay, here's a short sort of summary of what's going on with the 3. In a solid, you've got a fixed shape, all right? So the shape cannot change. In a liquid, it'll be the shape of the container. So whatever the container is, the liquid will just fall until it's evenly spread out, but, like in a beaker or something, it'll take up the shape of the container. A gas, on the other hand, will, in a given container, will literally spread out everywhere evenly, all right? And I'll go into that in a bit more detail later on. And second aspect of the properties of the different states is that solids and liquids, the volume doesn't change. They are incompressible. With gases, they can be compressed, all right? It's a big difference between the gases and solids and liquids. Okay, and as we just learned in the previous section, the densities, solids are most dense, so high density, and going to gases, the density decreases to low density, very low density with gases. Right, one exception, right? There's just one notable exception. Water. Okay, ice is less dense than water. And that probably is more in the field of chemistry in terms of why that is so. All right. It's to do with the structure of the water molecule and polarity, etc., etc. Don't need to go there in this particular video. But just remember that ice is less dense than water. It defies this particular rule. Almost every other substance will obey the density rule. Solids are most dense. Gas is the least dense. All right. Okay. Now, changes of state, effectively. Going from solid to liquid to gas. All right. This is how the substance will behave, the particles. In a solid, particles are fixed in position, okay, and close together. All right, so they are, very well packed together and very ordered. I think it's something I should probably squeeze in somewhere. So they maintain a certain order and a structure. They vibrate about a fixed position. So if you have particles sort of packed in like that, they're all vibrating like that, if you like, about a position, but they don't move around. They cannot move around. That's very, very important, fundamental to solids. Liquids, on the other hand, they are not fixed, all right, and they are still close together, but can move and flow. All right, so that's a big change from solids to liquids, and they move randomly about each other, around each other, if you like. Let's add that in. Around each other. Okay. And gases, finally, they are completely independent of each other. All right. They have no particular order. Or structure. So completely independent of each other, random motion. Okay. As you know, or you should know, Brownian motion comes up in questions. Okay. Random in all directions. And they have very high velocity or speed compared to liquids and solids, etc. Okay, now the last thing going from solid to gas is that solids have low kinetic energy because we've just mentioned that gases, they have very high velocity, whereas solid particles in their fixed positions, they vibrate but cannot move around. Okay, so they have low kinetic energy, and gases have high kinetic energy, and liquids obviously somewhere in between, but closer to the solid kind of kinetic energy level. All right, just a little diagram to explain what's going on there. Right, if you're adding energy, the solids, you can see they vibrate. All right, liquids still vibrate a bit more. All right, more vibration, and they have broken from their structure, so they can now sort of move around. This whole thing is moving around whichever way it wants. Gases, very high velocity, very well spread out, and completely random and independent. If you take energy out, so this way, going in that direction like that, you are adding energy, and this way you are taking energy out. So that's in and that's out. Energy out. Okay, removing energy. Right. One very important thing to note is that through a state of change, from one form to another, the mass must be conserved. Okay, you will not get questions and things where mass changes, so mass is conserved. Now here's a graph most of you are familiar with. On the bottom axis, we're showing time or energy. All right. I prefer to think of it as energy. As you add energy, you are increasing the amount of energy in the material. All right. But if the question or the topic you're looking at says that you're adding energy at a constant rate, then you can put time on the bottom axis as well. It serves the same purpose. What we can see in a solid, as you add energy, it heats up. Okay, up to a certain point when it will stop heating up, right? And the temperature is constant. During change of state. And that's twice, both here and here. Okay. This one is where it melts. And then it becomes a liquid, as you can see here. All right. And again, the temperature rises. Okay, so it's going up there, temperature is rising. Again, up to a point where it starts changing state into a gas, right? And that's going to be the boiling point. So it boils there or vaporizes, I think is probably the, let's put in the formal word, okay? And becomes a gas. If you then keep adding energy to the gas, again, that will also rise in temperature. All right. Now, the very important point to note about the temperature rises and the melting and boiling point is that the melting and boiling points, both of those, are very specific for each substance. And remember, that's often a test for a pure substance. So, e.g., water, it's exactly 100.0 degrees centigrade. All right. So, test for pure substance. If a pot of water boils at a different temperature, then it has impurities in it. All right. Now, the important thing to take away from that whole graph and discussion is that temperature remains constant whilst a substance is changing state. All right. And then once it is fully changed state, whatever amount you have, then the temperature will continue to change thereafter. And explaining that a little bit more, all right? We've already talked about that. Heating a substance increases its internal kinetic energy, all right? So the particles are moving around or vibrating, whichever the case is, more and more, all right? And that is why we get an increase in temperature. The more the particles either vibrate or the higher the velocity they have when they're moving around, flowing, the higher its temperature as we measure it. We've already talked about temperature remaining constant, so that's okay. Now the big question is why, all right? Why does the temperature stay constant? And I'll actually go through this in detail. As more energy is put in, the particles vibrate or move faster, all right, up to a point, okay? And at a change of state, the next bit of energy, all right? So if we go back to the graph for just a second, so you've gone, let's say, with the solid from here to here, all right? So you've gone there. This next bit of energy there, all right, that is going into kinetic energy, the first bit. This bit is going into separating or moving particles apart. Okay, that bit there, all right. And so effectively, the next bit of energy goes into separating the particles, all right, and not their kinetic energy, all right. So they're spreading out, all right. So no change in kinetic energy during that phase means there's no change in temperature. Now, just to explain that a little bit more visually, right? In a solid, if you had frozen carbon dioxide, all right, CO2, there you go. So in a solid, packed close together, all right, like that, and they're all, let's say, I don't know, vibrating a little, okay? So energy is contained within that order. Going to a liquid, the particles can move around and flow around each other, okay? But they are more separated, okay? And then finally, as a gas, they are completely independent and very spread out, okay? And so some of the energy goes into increasing their movement, and some of the energy goes into spreading them out. So as you can see, they are very far apart in as far as considering it compared to solids and gases, liquids, my apologies. Right, etc. Now to explain this, okay, the whole thing is explained in terms of internal energy. The energy stored in a substance, all right, is in the internal energy. It's in two forms, right? Two types. And one is energy in motion, energy in position, all right? The one in motion, the particles, when they're moving around, they have kinetic energy, all right? But the position is referred to as their potential energy, right? Relative to other particles. There we go. All right. So if the kinetic energy changes, temperature will change. All right. Kinetic energy is directly linked to temperature. But if the potential energy changes, then it'll cause a change of state. All right. That's how the two things are related. Kinetic is temperature, and potential is to do with the change of state or the state they're in. The amount of energy on this side needed to change the temperature is indicated by the specific heat capacity of a substance. All right. So that symbol is just C, all right? Specific heat capacity there. And that basically is defined as the amount of energy needed per kilogram per degree Celsius, if you like. So that means if I have a kilogram of water, how much energy do I need to increase that kilogram of water's temperature by 1 degree? And for water, you're looking at, actually, no, I'm not going to confuse you with the values, but it's 4,200 kilojoules, all right, per kilogram. One second. Should I write it like that? Per degree Celsius, all right? And it's obviously, quite a chunk of energy going in there. Right. On the other side, before I move on to the equations and things, similarly, there's a measure of how much energy required to change state in from either solid to liquid or liquid to gas. It's a specific latent heat, it's called, right? And symbol is L. There were two. There's an LF, right, which is the measure of fusion, so when it's melting, okay? And LV, subscript V, is vaporization, okay, boiling. So that's two words that you need to know. If, and I need to mention this before we move on from there, is that if the process is going in reverse, so for example, you're going from a gas to a liquid, then that would actually be the same energy as vaporization, but you're, in this case, giving the energy out rather than taking the energy in. So a negative calculation, all right? But the number actually remains the same. It doesn't matter whether it's going from liquid to gas or gas to liquid. The amount of energy change will be the same, but you have to consider whether the energy is going into the substance or coming out of the substance. All right? So, okay, coming back to the calculations now. What we, bear with me a second, just going to check if I've done that one correct. Yep. Right. The specific latent heat, yeah, energy is required per kilogram. Remember that there's no energy change in terms of kinetic energy, so no temperature change during a change of state. So it's simply the amount of energy to change the form of 1 kilogram of material is the standard measure. And right, coming to the actual calculations and what you need for that. Right, so here the total energy for the specific heat capacity, what we have there is that the total energy input is the mass times the specific heat capacity, all right, times the change in the temperature. Okay, and that I think is fairly self-evident, right? M for mass, so you need kilograms, and the specific heat capacity of any given substance. If it comes up in a question, then that will be given to you, all right? Even if it's water, they'll give that to you. And change in temperature, okay? On the other side, the specific latent heat, the formula for that is simply the amount of energy required is mass times the latent heat, so the total mass of the substance you have, and the latent heat for whatever change of state you've got. Either, first of all, this one is a solid to a liquid, and this one is going to be a liquid to a gas. All right? Okay. Oh, I've just spotted a mistake, and I want to correct that before I move on. That should not be kilojoules. Okay? Let's just clarify that before I get anybody complaining. Water, all right, the specific heat capacity of water, as an example, is 4,200 joules per kilogram per degree Celsius. So, for example, if I had half a kilogram of water, right, so let's say M equals 0.5 kilograms, and I want to heat it up from 20 degrees to, let's say, 90, probably about right for a cup of coffee, then the amount of energy required will be your MC delta theta. So that's going to be 0.5 times 4,200 times 70. All right. And I don't know, should I grab a calculator and actually give you the number for that? Because water actually has a very high specific heat capacity compared to a lot of other substances. So 0.5 times 4200 times 70, and there you go, 147,000 joules, or 147 kilojoules. In those calculations, either form of answer is perfectly acceptable. All right. Okay. I want to reverse back to one thing, and I want to really emphasize this point. Okay, and I'll put it in a different color, I suppose. Very, very important point. When we have a change of state, yeah, we are not breaking bonds. Very important. Often that's the most common mistake, all right? We are not breaking bonds. What we're doing is overcoming attraction forces between particles and separating them. Okay, that is really important. Okay, do not write we're breaking bonds, because think about it. If you were to break bonds, what would happen, right? When you're heating up, let's say, carbon dioxide, you don't suddenly get carbon dioxide becoming carbon plus oxygen. Yeah, that does not happen. Okay, if you were to say you're breaking bonds, then that's what would happen. And that is not true. So do not use that language. Talk about overcoming attraction forces or intermolecular forces, if you like, between particles. Okay, hope that's clear. Right. Finally, this is a bit that if anybody wants to, they can skip out of the rest of this if it's not necessary for your particular exam this year. But moving on, gases and pressure. All right, a gas in a container exerts a pressure on its surroundings or walls of the container. All right, and the reason that happens is the particles are colliding with the surfaces and exerting a force, right? Because there's a change of momentum. The particle hits and then bounces back, all right? And that change in its motion effectively puts a force on the wall itself. And as you know, pressure is force over area. So that's newtons over square meters. Again, units, all right? And the unit of pressure, i.e. 1 Newton per square meter, is a Pascal, all right? And atmospheric pressure and things like that are all stated in pascals. Now, very basic aspect of this is if temperature increases, right, particles will move faster. All right, so temperature increases, particles move faster and collide with walls more often and with more speed. Okay, so both of those things will happen. Okay, and therefore the total force increases, right, over the same area, and therefore the pressure increases. All right, so same amount of force over the same area would be the same pressure. But if, for example, we have twice the force over the same area because it's the same container, then obviously pressure increases. All right, simple concept there. Now, one aspect of pressure in a gas, due to Brownian motion, all right, particles move randomly in all directions. And you remember the Brownian motion experiment or demonstration. In a glass cell, you got smoke particles, and you look at it under a microscope, etc., and they are whizzing around in all directions randomly. All right, so particles move randomly in all directions. Therefore, pressure in a gas is equal, all right, in all directions. All right, there's no difference whether it's in a liquid or indeed a gas. Pressure is exerted at any given point equally in all directions. And finally, to finish up, right, two rules, pressure rules that you need to know. We've already demonstrated that pressure is proportional to temperature. So that means pressure over temperature, okay, is constant at a constant volume. All right. So if temperature goes up, then pressure must go up. All right. The second rule, okay, so that's your first one. Second one, pressure is inversely proportional to volume. Okay. So if you increase the volume, then the pressure goes down. If you compress a gas, i.e., you reduce the volume, then the pressure will go down. And the rule for that is that pressure times volume is a constant, okay, at constant temperature, as long as the temperature doesn't change. In the previous one, pressure over temperature is constant, again at constant volume, all right? And just to explain that second one, the one that is referred to as Boyle's law, all right? If you compress a gas, the particles have a shorter distance to travel between collisions, okay? Therefore, there are more frequent collisions, right? i.e. more collisions in the same amount of time, and therefore increased force, more force, and therefore the pressure increases. Now, I realize that may not be examinable this time, but for those of you who might be then moving on to A-level physics, it's something worth coming back to later and looking at it, if it's not examinable in your particular exam this year. but these principles come up in a very, very big way in A-level physics later on. Right, so that's everything covered, and I think I corrected that mistake with the kilojoules. Yep, so that's fine. Right, if anybody has any further questions on this topic or would like any clarification or even any particular problem solved, practice questions, etc., please drop it in the comments. If you found it at all useful, it'd be great if you subscribe, switch on the notifications, because I'll be doing a few more videos on the physics paper 1 material, and hopefully over the next day or two, and indeed other science and maths papers. Right, thank you very much for watching, and those of you with exams, very best of luck. Take care. Bye-bye.